Hi, my name is AG Ramesh from Intel, and joining me today will be Andres Rodriguez, also from Intel, and Penporn Koanantakook from Google. We'll start off with Penporn talking about TensorFlow.
Thank you so much for the introduction, Ramesh, and for having me here today. Now it's my turn to introduce TensorFlow. So TensorFlow is an end-to-end open source machine learning platform by Google. We have a rich ecosystem of tools that helps machine learning developers build and deploy their models and also helps researchers push the boundaries of machine learning. It is widely used around the world. Here's some maps of some of our GitHub stars that self-identify their locations. To date, TensorFlow has been downloaded over 200 million times and has more than 52 million tutorial and guide views. We have also recently passed the 1 million online learners mark on open online courses like Coursera and Udacity. Intel and TensorFlow has been collaborating closely for over 4 years now, which is a long time considering that TensorFlow is turning just 6 years old in 2 weeks from now. There have been a lot of interesting work done, but our favorite ones has to be the ones where we add support for new hardware feature to TensorFlow. So here's the outline of the talk. I'll start with giving an overview of the overall optimizations. Then we'll talk about our work in 2019 on adding quantization support to TensorFlow CPU ops to be able to use the int8 vector instructions launched with the Cascade Lake CPU. Then we'll talk about the year 2020, where we add a new data type support, bfloat16, to TensorFlow CPU as well, just in time to use the new bfloat16 vector instruction debuted in Cooper Lake CPU. As for this year, we co-architected PluggableDevice, a new mechanism to add support to TensorFlow as plugin packages. Then at the end of this talk, we'll give you a little sneak peek of our current work on supporting the new advanced matrix extension instruction coming out next year. So all these timely hardware support wouldn't be possible without the OneAPI Deep Neural Network Library, or OneDNN for short. OneDNN is an open source performance library of basic building blocks for deep learning applications. It supports standard IEEE floating point 32 and 16 bits, as well as newer data types like bfloat16 and int8. And it is developed and maintained by Intel, so you can count on it having support for any latest features in Intel hardware. For example, it can use Intel DL Boost and AVX 512 instructions. It is cross-platform. It can run on Linux, Windows, Mac OS, and it supports a large array of hardwares, including Intel hardware, ARM CPUs, NVIDIA GPUs, and so on. So the basic building blocks it supports ranges from compute-intensive ops like convolutions, matrix multiplications, and RNN ops, to memory bandwidth limited operations such as pooling, batch normalization, and so on, to data manipulation ops like reordering. It also supports fuse operation for better performance optimizations, which I'll talk about in the next slide. So here is how we integrate OneDNN with TensorFlow. So we start by creating custom OneDNN ops that are responsible for calling OneDNN primitives. And then at runtime, we replace applicable standard TensorFlow ops with these custom OneDNN ops. We also apply aggressive op fusions for even more performance. So op fusions is replacing commonly used subgraphs of a lot of ops to just one big fused ops. Like the figure here, for example, this is a subgraph from BERT, a popular language model. And OneDNN can replace this whole subgraph with just one big fused op on the right here in the figure. So fusing ops has an advantage of improving data reuse because you can now do more computation on the same data block while it's still hot in cache. It also improves kernel launch and synchronization overhead as well. To use OneDNN primitives, there is actually an overhead of creating those primitives. So we also add a cache to TensorFlow to reuse all those primitives as much as possible to reduce the overhead. So here is a preview of the performance. So Previously, these OneDNN optimizations were only available in a separate Intel optimized TensorFlow packages, but now we're very happy to tell you that these optimizations are also available in standard TensorFlow packages. But it's disabled by default, but you can turn them on by setting an environment variable tf enable OneDNN ops equal to 1. And just by setting this one variable, you get the speed ups shown on the right here. So the graph here are latency and throughput improvements comparing turning them on with turning them off. And we see significant speed ups over a wide range of models ranging from image recognition, object detection to language models. And for some good case, we saw up to 3x performance improvements. These optimizations are also available in packages that depends on the TensorFlow package, like TensorFlow Serving, TensorFlow Extended. And if you are wondering if you will be able to remember this long variable name, we have some good news for you. We are considering enabling these optimizations by default, so people will be able to use this without having to set any environment variable. So we have recently published a request for comment or RFC for this in the TensorFlow community repository. And if you have been using these optimizations in the default TensorFlow packages or are considering doing so, we would highly appreciate your feedback.
Thanks, Penporn. Now I'm going to be talking about some of the optimizations that we have done in TensorFlow using low precision data types. Firstly, I'll talk about 8-bit inference optimizations. Quantized models are becoming more popular for deployment nowadays. And basically, a quantized model is a version of the FP32 model that uses 8 bits instead of 32 bits. The advantages of using 8 bits is that the models are much smaller, so it saves on memory bandwidth. And further, we can do some optimizations to accelerate some of the computations. The process of converting a trained FP32 model into int8 is not straightforward. It involves an additional step of quantization, and quantization uses a small calibration data set to compress the weights from 32-bit to int8. And also the graph or the model is modified to use int8 for activations instead of the standard FP32 data type. We have a tool, the Intel Neural Compressor, that does a lot of this automatically. It replaces the model with int8 operators wherever possible and adds some additional layers that would then take the standard FP32 input and converts them into quantization. And once as the data flows through the model in int8, at the end it inserts another dequantize to return to turn the output back into FP32 that the user would need. As I mentioned before, there's lots of performance optimizations using this model, using quantized models, and specifically the DL boost instructions in the Intel Xeon CPUs have specific acceleration that can accelerate 8-bit computation significantly. So now I'm going to show you a demo of how Intel Neural Compressor works. So this is the web-based UI that's provided by the tool. The tool allows you to configure your own quantization scheme, or you can use a preset one that's created by the tool. So here we're going to use our own method to quantize. So we click on the wizard. We pick the model file. This is the pre-trained FP32 model. So here we're going to be quantizing the SSD ResNet model. So the UI is very intuitive. It selects default values. It selects default values for the input and output. You can change them if that's not correct. And by default, it also selects the int8 quantization. So now you need to select the evaluation data set. You can do that. So we use, since this is a SST model, we use a COCO data set. And also we specify that the tool needs to use the same data set for calibration. So instead of using the entire data set, it just uses the first 100 entries. You can do some additional transformation. The tool automatically picks some appropriate transformations, but you can add your own if needed. And you click finish, it starts the process of quantization. So it goes through several iterations trying to find the best match between accuracy and performance. This could take some time as it goes through the computation. Typically, it takes a few minutes. Yeah, now it's done. So it's finished quantization, and it's placed the output, 8-bit output, in a file, and it also prints statistics on how good the compression was. As you can see, with an accuracy loss of very small accuracy loss, you get about 4x improvement in performance. And in addition, the model size also has reduced by 4 times. So let's look at some of the performance that you can get using the Intel Neural Compressor. So we took a few examples of popular models using object detection or image recognition and language modeling, and we compress those models and quantize them using the Intel Neural Compressor. So you can see on the right, there's significant performance improvements across all these models. So you can get about 4x improvement, up to 4x improvement in performance. And most important thing is the accuracy loss that we saw was very less, so less than 1% accuracy in all these cases. So you can use the Intel Neural Compressor to compress your own models, or if not, you can get most of these pre-quantized models using the Intel Model Zoo. So now I'm going to be talking a little bit about bfloat. So bfloat is a 16-bit data type that's in TensorFlow. It uses the same range as FP32 operations, and this gives us certain advantages compared to the standard FP16 16-bit data type. One of the advantages of using 16-bit data types is that the bandwidth, because the size is about half the size of FP32, you get a lot of bandwidth optimizations that you can do. And in addition, most of the hardware now, including the Intel CPUs, have specific accelerators that can compute bfloat 16 directly. So you get a lot of performance benefits when using bfloat 16. So, for example, on the right-hand side, you can see that on the Intel Cooper Lake processor, we can see about 2x improvement in performance, both on training as well as inference. At the same time, we saw only about a less than 0.2% drop in accuracy, which is almost negligible in most cases. Another advantage of using bfloat, unlike FP16, is that you don't have to do any of the loss scaling in the backward pass because the range of the bfloat 16 is very close to FP32. There's no need for doing most of these. So this makes converting a model to bfloat 16 much easier. And further, we've seen that the hyperparameters that you use for training on FP32 carry over without any changes to bfloat 16. So this makes a lot easier to convert the models, your existing FP32 models, to bfloat 16. So how are you going to use this in TensorFlow? TensorFlow has the feature called auto mix precision. So it basically this takes a FP32 model and converts it into bfloat and adds casts wherever it's needed. So that to convert an FP32 to bfloat and back. So and the AutoMix Precision automatically adds these, so it's nothing much for the user to do. These AutoMix Precision techniques work both on the traditional or classic graph-based models as well as the keras-based models. So here's an example of how you would be using this, using AutoMix Precision with TensorFlow. It's very straightforward. So if you have a keras model, all you need to add is a couple of lines of code to set up the AutoMix Precision settings, and then it's just a few additional lines of code to enable it. So this is the preferred method for enabling bfloat. But if you have older models that are based off graphs, you can also use the grappler-based AutoMix Precision grappler options. So now we talked a lot about the past work that we have done. We have a lot of interesting things happening right now. And I'm going to hand it over to Penporn first to talk about some of the new changes that we recently added to TensorFlow.
Thank you, Ramesh. Now we'll switch gear and talk about AI accelerators for a little bit. So before this year, the only way to add new device support to TensorFlow is by adding the code directly into the TensorFlow core repository, and that's not very scalable. It adds significant overhead in both development, testing, and also maintaining. So in TensorFlow 2.5, Intel and Google has co-architected PluggableDevice, a new mechanism that lets developers add new device support to TensorFlow as plugin packages without needing to make any code change to TensorFlow core. So this mechanism consists of four new major components. So the first one is a new device type in TensorFlow called PluggableDevice. And the rest three are C APIs that lets device plugin talk to different parts of TensorFlow in a stable manner. So Intel has been a huge contributor to all this support, designing and implementing 3 out of the 4 major components, and we highly appreciate Intel's help for this. And this new mechanism is very scalable, and it opens doors for many new device integration to TensorFlow. And one of them is definitely, of course, Intel GPU device. So Intel is developing an Intel extension for TensorFlow plugin that will let users use Intel GPU seamlessly with their existing models without needing to change the model. And this same plugin package will be able to support Intel XPU devices as well, thanks to OneAPI and OneDNN abilities to support all of those. Apart from Intel accelerators, there are also other people in the community that adopted the PluggableDevice mechanism. So in June, Apple recently released the TensorFlow Metal PluggableDevice plugin for Apple GPU support. And currently, we are also working with Microsoft on the TensorFlow DirectML plugin for GPU support on Windows. So next, Andra is going to give you a really highly anticipated sneak peek of AMX and the Sapphire Rapids CPU.
Thanks, Penporn. Another great feature that I'm very excited to share with you is the 3rd generation of Intel Deep Learning Boost. On the top, you can see those 3 rectangles. The first 2 represent the 1st and 2nd generation of Intel Deep Learning Boost already available in production. This accelerate the performance of Int8 and bfloat 16 by 4x and 2x respectively. In the next generation of Intel Xeon scalable processors, codename Sapphire Rapids, we introduced the 3rd generation, which significantly boosts the performance of these data types. On the bottom right, you can see the gains over FP32. So in the number of operations per clock cycle per core is 1024 for bfloat 16 and 2048 for FP32. This is essentially 16x performance gain over FP32 or single precision and 32x with Int8. So how do we do this? So on the left, you can see a high-level description of the Intel Advanced Matrix Extensions of AMX. And AMX has essentially two main components. One is tiles, and the other one is TIMO. Tiles are essentially two-dimensional registers, which are 16 rows of 512 bits or 64 bytes. And tiles and the regular registers, the data is transferred via the regular memory hierarchy. Then TIMO accelerates the multiplication of the data in the tiles. So TIMO consumes the tiles, performs matrix multiplications, and accumulates to 32 bits of precision. Let me share some early results by using AMX. Here you can see the performance gains from the third generation of Intel Xeon Scalable processors, codename Ice Lake, all the way to Sapphire Rapids. You can see a 30x performance gains from both the software and hardware improvements. So on the left, for this model, known as SSD ResNet 34, used for object detection, you can see the baseline of TensorFlow with FP32 on Ice Lake. We measure around 13 samples per second throughput. When you add OneDNN acceleration, just in software, you get a 1.5x improvement in performance. Then when you use the Intel Neural Compressor to quantize your model to 8 bits, you get an additional 3.9x of performance. Today, we are measuring on pre-production Sapphire Rapids already a 4.x additional performance gains. So from all those performance gains accumulates to 30x in one generation of Xeon Scalable processors, one generation jump of Xeon Scalable processors.
Thanks, Andres. It was an interesting presentation. Now I want to summarize what we have talked about so far. As you saw, we showed you how we've improved TensorFlow over the last 4 years and added lots of different optimizations, including multiple new data types, optimizations for multiple new data types. We also showed you that you can enable these very easily using one environment variable that needs to be set. As Penporn mentioned, we have a RFC out there. Please take a look at it and provide comments on that. We talked about how to quantize models, and we saw a demo and some performance improvements that you can get if you are doing inference. We also discussed how to use bfloat16 on the Intel Cooper Lake processors and the performance benefits you can get both for training and inference. And Anders just mentioned about some of our upcoming platforms using the Intel AMX and the additional benefits that you can get both for int8 and bfloat computations on Sapphire Rapids. Here are the additional links that shows you how to use the Intel Neural Compressor tool or Mixed Precision. Please take a look at them and provide us feedback. Thanks.